Hello everybody. Let's debrief these families of polar curves that you explored in class. So pedal people explored curves that looked like cosine or sine of some positive integer multiple of theta. So here's an example of cosine 2 theta and cosine 3 theta. And people noticed that when the coefficient here was odd, it exactly named the number of pedals. So 3 matches with 3. When the coefficient was even, the number of pedals was double. And so we were interested in why does that happen, what angle do the pedals face at, and potentially other questions as well. The loop group was interested in families that look like some constant plus a scale factor multiplied by sine of theta. And as you can see, as k changes values, sometimes you get a circle, and then sometimes you get a loop. So we're interested in when does the loop happen, why does the loop happen, what angles does the loop happen at, and then what's the height of the loop. So notice that when k equals 5, the loop hits 3, approximately 3 there. So we'll start by debriefing pedal people. Here is a graph of y equals sine 2x. Here's a graph of r equals sine 2 theta. So if you treat these points as if they're polar, you get that graph. So x coordinates here correspond to angles here. Y coordinates here correspond to radii here. So it's helpful to plot individual points. It's also helpful to think about intervals. So this interval where the angle goes from 0 to pi over 2, that's this interval where the angle is 0 pointed right to pi over 2 pointed up. So you can see I've marked it A here. So this kind of horizontal interval A matches this quarter circle of angle values. Okay, I see that all the heights here are positive, which must mean that for all of these angles in this direction, the amount that I move is in the direction that I'm pointing, because positive r means I'm moving in the direction I'm pointing. So you see my r value goes up a little bit, up a little bit, up a little bit. So here I go up, up, up until this point right here corresponds to the end of the pedal. So we've already answered one question: what angle do pedals happen at? All you need to do is look and see where the maximum radius happens, because it makes sense that that's where you should be the furthest distance from the origin. So that would be the middle of a pedal, this would be the middle of a pedal, and so on. Okay, so notice this is marked 1 and that's marked 1. That's because this part of the rectangular curve corresponds to that part of the polar curve. But this next part doesn't match that part. So if I was going to imagine graphing this just as the angle slowly increases, it doesn't graph this way. It doesn't go boop, 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 boop. Even though in the graph you see the angles are continually increasing, like up to pi over 2 and then through quadrant 2 to pi and so on. So what's going on is in this interval of angles, b, which corresponds to pi over 2 facing up all the way through to pi facing left, all of the radii are negative, which means that if I'm facing in this direction instead of walking in the direction I'm facing, a negative radius means that I'll walk in the opposite direction. So all of these values down here are actually plotting over here in quadrant 4. So that's why I've marked 2 right there. And in particular, if we imagine 3 pi over 4, which is pointing 45 degrees that way, I'm going to move a distance of negative 1. But if I'm facing in this direction, it'll be negative 1 in the opposite direction. So this point here corresponds with that point there. Okay, so that's what's going on. Let's take a look at it animated, because that may add something to your thinking. Okay, so I'm going to animate drawing the shape. Let's just watch it once first. So this rotating green line is showing all the angles slowly increasing from 0 to pi over 2 to pi all the way around. And then this dot is showing what point actually gets plotted if I move either a positive distance in the direction I'm facing or a negative distance in the opposite direction that I'm facing. Okay, so let's just look at it kind of slowly here. So if I go from 0 to pi over 2, I am moving in the direction I'm facing. So you see it's in green, and the point is on the line that's showing me the angle I'm facing at. So there's pi over 2. If you remember, for the next interval from pi over 2 to pi, the angles are facing through this quadrant too, from pi over 2 straight up to pi left. But the points are plotting in the opposite direction, which is why that petal plots over in coordinate 4. Now I'm back in, here let me see if I can display the other one. Next I'll be plotting this interval where I'm in quadrant 3 and all the distances are positive again. So the question here was, what causes this loop to happen? So this is a graph of 2 plus 4 sine x. This is a graph of 2 minus 4 sine x. Here's the rectangular version of each graph. Here's the polar version of each graph. So this phenomenon with the loop is also caused by negative radii. So here, this entire hump corresponds to angles that are pointed up in the upper half of the circle. So they're pointed this way. And so that's what's drawing all of this up here. If we look at the bottom half of the circle, we start off with a few positive radii in the bottom half of the circle. And that's what's happening right here. You see that if I'm pointed at this angle, I still have to move in the direction I'm pointing to get to the point on the curve. But there's a certain angle here that's just a little bit less than, let's see, 1, 2, 3, 4, 5. So this direction is 5 pi over 4. So it's just a little bit less than 5 pi over 4, where the radius is going to hit 0. And that's when we hit the origin there. So here would be 5 pi over 4. So you can see a little bit less than 5 pi over 4, the heights hit 0, which means the radius is 0. So that's the moment at which our curve hits the origin and is about to start drawing this loop. As the angle points downwards, this whole series of downward pointing arrows, that corresponds to all of these angles here, which have negative radii. So instead of moving in the direction that the arrows are pointing, I move in the opposite direction, and that draws that little loop until we get to the next time that the radius is 0, and that's when we kind of exit the loop. Okay, this one is almost the same. The only difference is here the loop drew when the angles were pointed down in the second half of the curve. Here, the loop draws in the first half of the curve when the angles are pointed up. Because if I have an angle that's just slightly less than pi over 4, that's pointed in this direction, up. But then I'm going to be plotting in the opposite direction, and so they'll plot down here. And then the large loop is all plotting, walking in the direction my angles are facing, in the part of the curve where my angles are facing down. Okay, so let's do kind of a check your understanding question. Sorry, before we do that, let's look at it in Desmos. So here's what we just talked about animated. So when the angles are facing up, we just draw, in the direction that we're facing. Now, the angles have got, or the radii have gotten smaller and smaller and smaller until we hit this special angle where the distance in that direction is 0, and so we hit the origin. And now we're plotting the opposite direction until we have a radius of 0 again, and then we start plotting in the direction that we were facing. So that's the full loop with the loop. And now let's do the actual check your understanding question. So if I was going to graph r equals 5 plus 11 sine theta, what would be the height of the loop? Well, let's go back for a second. here, the height of the loop would be like that distance. And so I'm interested in what point has the largest radius in the section that draws the loop, and that would be this point. This is 2, whoops, let's redraw this. This is 2 plus 4 sine x. I know that sine x, the smallest thing it can be is -1. So let's pretend sine x is -1, and we know where it's happening also. This isn't, the frequency hasn't been changed, so this is at 3 pi over 4. Nope, this is at 3 pi over 2, because it's facing straight down. So when it's facing straight down, sine is -1, which means I'm at 2 plus -4. So that must make this point down here -2. But if I'm facing down and I plot a distance of -2, that takes me 2 up. So the height would be 2. So the height is just that total distance. All right, let's use that same idea here. So if I was going to plot 5 plus 11 sine, what would it look like? Let's imagine it as rectangular first. So let's say that's 5. 11 is the amplitude, so that means I'd be going up by 11 and down by 11. My drawing here is probably not to scale. So 5 plus 11 is going to be 16. 5 minus 11 is going to be -6. So if I was going to plot this, it would look something like this. And I know that this part with negative radii is what would draw the loop. And I know that the part of the loop that would be the furthest away from the origin would be here, and it would have a height of 6. So, this is going to be a very rough graph here, but probably it's going to look something like this. We start at a distance of 5, and then we go all the way up here to 16. So that's 5. That's -5. So 5 goes all the way up to 16, then back down to 5 again. This should be symmetric, even though I didn't draw it that way. Then the radii go to 0, and then we're going to draw a loop that makes it all the way up to 6, and then back out again. Something like that. Okay, so satisfying curiosity, let's just see how badly my drawing went. Okay, here's 5 plus 11 sine theta. We go all the way up to 16, back down to 5, draw a loop up to 6, and then back.